Okay, everyone. So today I want to talk about this paper that just came out. I believe, yeah, it came out. I mean, 4 days ago now. Um, and this paper is called the Hardware Lottery. And what it's really about, I'll just give you some quick background as to why I'm reading this paper, why I think it's interesting, and why I want to discuss it on stream. So basically, the main idea, and so here the term Sarah is using, it's called the hardware lottery. But in the past, like I would personally refer to this effect in the past as hardware reflexivity. What do I mean by that? So let me just say this like so hardware reflexivity, and so the idea of reflexivity. This I'm borrowing from like the really famous investor George Soros. And so the idea there is that your beliefs influence the world, which in turn influences you. And so let's take an example. For example, like if you believe, uh, you know, if you buy Amazon, it goes up, and then you buy more Amazon. Uh, or like in more detail, like let's say you have a belief that Amazon is really valuable, you'll buy more Amazon shares. Amazon does indeed become more valuable because it has more capital it can deploy efficiently. And so again, like this is where this idea of reflexivity comes in. So what does hardware reflexivity mean? So what hardware reflexivity means is that like in algorithms typically, we have a notion that some like algorithms sort of fall into two very broad buckets. So there's like fast algorithms and then there's slow algorithms. Uh, but really fast and slow. So let's say so really the running time basically of an algorithm is a function of both the algorithm and the hardware. And so why is that the case? Because like different kinds of hardware excel at doing different kinds of tasks. And so specifically, like let's say I just want to show you this quick example, like this MemD versus MD Wikipedia. Here we go. So for example, like when we think of something like I think if you're listening to me, like odds are you're interested in machine learning in some shape or form. And so, for example, like GPUs, like their programming model is called single instruction, multiple data, as in you do the same kind of instruction again on multiple data. For example, matrix multiplication. Uh, you're doing the same operation on every row and every column, like on every element, you're doing a dot product. So this is a single instruction. But what changes is the actual data. Like what changes is what's inside your matrix. This is actually very good for machine learning because, for the most part, machine learning is a series uh, of a composition of dense matrices. And what that means is that, like, if you like a matrix, is really a matrix is a linear map. So, as in a matrix is a function, the composition of a bunch of these functions can be viewed as a neural network. And so, it's no surprise that GPUs are very commonplace when it comes uh, to doing machine learning problems. Like when you think about it, like, well, how much of this is actually due to the actual algorithms that we're using in machine learning like the fact that they're actually good and maybe the best algorithm, and how much of that is due to, uh, the algorithms, these specific algorithms just running really fast because we've invested a lot of time, energy, and resources in making GPUs really fast. So this tells us a few things. Like, like on one hand, you could think, well, what about different programming models? Like, let's say multiple instructions, multiple data, where you could do completely different things. And this is sort of what I work on at GraphCore, for example, like in IPU related stuff. Like, this is our programming model. And so then we tend to think, great, like what kinds of algorithms work well here? And, at a high level, stuff that involves sparsity or sequential algorithms like RNNs tend to do better than dense matrix multiplies in GPU. But what else? Like, I mean, even if we were to just say something like, you could take this super simplified model, like a single instruction, single data. So there's like extremely specialized hardware. Or it could be multiple instructions on the single data stream, and you can think of this as a pipeline where you're operating on some form of data and doing a bunch of operations in a sequential nature. So stuff like I mean, I think Spark is general purpose, but just this idea of pipelining is misty. Um, so great. I mean, so that's sort of the background. I think like all of the background that you need to probably understand the rest of it, the rest of the stock. But I thought like it'd be helpful to go over the paper. Like this is the depth of my knowledge as far as this stuff goes. But I think like the author here, so uh, so Sarah Hooker wrote like a bunch of really interesting examples, and I believe she's probably thought about this a bit more deeply than I have, and so I'm just really looking forward to going over this. So yeah, I mean, without further ado, let's just do this. Um, so she's saying basically hardware and software determines which research ideas succeed, and she uses the term hardware lottery to describe when a research idea not because it is suited, but because it is superior to alternative research directions. So this is I mean, I think like what I find interesting about this characterization is that really, like if you were to think, like let's say this is some space of optimal algorithms. Like, well, if the actual space looks like this, maybe GPUs are here. Like maybe GPUs aren't actually here. And sort of if you view it from this concept of a landscape function, then it also becomes interesting when you think of it. Like, how do you know that what you're doing is actually the best thing possible? The real answer is you don't. But at least you could sort of think about these things conceptually and say, well, like hypothetically, if I did have hardware that could do this really fast, like what kinds of interesting algorithms can I do? And that's sort of, I think, one of the compelling things about the MIMD architecture. So, compelling examples from early computer science illustrate how hardware lottery can delay research progress by casting successful ideas as failures. So, these lessons are particularly salient given the advent of domain specialized hardware, which makes it increasingly costly to stray off the beaten path of research idea. So, this essay posits that gains from progress in computing are likely to become even more uneven, with certain research directions moving on the fast lane while progress in others is further obstructed. So this is interesting. So um, as far as this last line goes, what I find interesting about it is like I don't know if like some research directions will become impossible because current hardware doesn't exist for it. I think that's probably a bit too bleak of a future as far as I'm concerned. Like the way I would see it is like the best ideas win in the long run. It's just that decent ideas can survive for a really long time. And by really long time, like this could be hundreds of years. Like, I mean, here we're talking over like generations of people's understanding of how these techniques work. So it's not something we would expect to just be resolved overnight. But anyway, like, so going through the paper, um, yeah, so what's interesting is the first person she quotes is Kuhn. So if you're not aware, Kuhn wrote a book called The Structure of Scientific Revolutions. Uh, and in it, sort of the main idea that he talks about is that whenever there's something that's a paradigm shift in science, like you would expect scientists to make decisions based on logic or data. Often they don't. Often they get attached to their opinions in an extremely religious way, and anyone who doesn't have these opinions ends up being called a heretic. And so, controversial ideas end up invariably getting really delayed, whereas like incremental ideas are very easily accepted because there is an easy metric to accept them for. For example, in the case of machine learning, if you were to make a transformer model either smaller, faster, less memory, like you're going to get published. Like these are all very practical ideas, they're very useful. However, if you were to come in and say, well, I don't know if this is the best architecture, here's this other newfangled architecture I came up with. It's not exactly state of the art, but it looks kind of cool, doesn't it? Like this is unlikely to be published. It's much more likely to be a blog post or something that you share with your friends. There are a few exceptions, of course. Like there's people like Hard Maru that publish like these really weird ideas, and he still like does a good job of seeing them through and getting them published. But again, it's in the minority, and most people would succeed more from incremental work. And so we get to this straight off where doing incremental work is just more beneficial for your career, straight up. And the idea is that like it do taking risks really only pays off for like a small subset of people. And so this sort of tells you, I mean, this sort of gets back to I think something that Nassim Taleb talks a lot about in his books, which is called like the barbell strategy. So as in here, like you want to be sort of biding your time between incremental work and then take risks. Like you don't want to do work that's half half. Like you want to do work that's guaranteed to pay off, and then you want to do work that's guaranteed to pay off big if it works out, but has a low probability of doing so. So I would say this applies not only to just researchers. I think even if you're like an industry person in ML or just like any sort of regular employee in any field, I think this is a great way to sort of think about how you should allocate your time. More practically, one thing I like doing is I tell myself, like, Fridays is for new ideas, and this is an idea I borrowed from Richard Hamming from his book, where he refused to take meetings on Fridays. Sorry, I don't know why my nose is so itchy, but yeah, he refuses to take meetings on Fridays to just do, like, wilder stuff. So anyway, uh, so what follows is part position paper and part historical review. So we argue that choices about software and hardware have often played a decisive role in deciding winners and losers in early computer science history. So after decades of treating hardware and software as separate choices, the catalyst for closer collaboration include changing hardware economics, a bigger is better race in the size of learning architecture, and the dizzying requirements of deploying machine learning to edge devices. Um, so closer collaborations, okay. Changing hardware economics. What is this paper about? So Hennessy is like the computer architecture guy. Let's see. So many references. Oh, interesting. Okay. Okay. So the end of Moore's law is interesting in a few ways. Like, so basically, if you can imagine that, like, for the longest time, like, Moore's law was that essentially the number of transistors would double over time. So basically your compute power doubles over time, and this gives you an exponential curve. This curve is no longer true. So instead, what you need to do to sort of keep up this pattern is you need to do async, you need to do distributed, you need to do multiprocessing. Uh, what else? Like, so the async distributed multiprocessing, ASIC, so sort of domain specialized hardware, and of course stuff like GPUs, and even more recently stuff like IPUs. So it's not because Moore's law is over that we're just done. It's more that, like, now we have to get more creative, and the kinds of problems we're working with becomes fundamentally harder to work with and debug. Because you're not just running something on a single machine. Now you're just working with a cluster every time you're doing something little, even if it feels little, it's often still fairly complicated in the way it works. So, all right. So the bigger is better race. I mean, I would imagine this is something more people in machine learning are especially aware of, like the fact that models like BERT and GPT exist, and that you can continue scaling them, and that trend doesn't seem to be, at least right now, to be stopping, despite what people think. Like, I mean, even if it makes people uncomfortable because it doesn't feel smart, it works. And so this is just something that's a bitter pill that we sort of have to accept, and I believe a lot of people have accepted in the community. And the dizzying requirements of deploying machine learning to edge devices. I mean, yeah, so there's a couple of points here. Like, let's say with edge devices, it's hard to update models. It's hard to load them because your device doesn't have as much memory, especially if this is like a little chip, not something that's like a phone. The inference is slower. So, like, let's say you're calling a service, and then, or you need to send some sort of data to a service, but you're in a place with a slow internet connection. So these are all reasons that make, like, deploying machine learning to hardware particularly challenging. So have centered on a wave of new generation that is domain specific to optimize commercial use. So while domain specialization creates important efficiency gains, uh, it arguably makes it even more costly to stray off the beaten path of research ideas. Oh, interesting. Yeah. So I actually like this point. So basically, like, I think what she's saying is, like, well, like let's say deep learning doesn't end up becoming huge, or I mean, sorry, like, it's already huge. Like, let's say deep learning isn't huge in 10 years, and you invested all this time today making the main specialized hardware for deep learning and neural networks. You're just gonna end up with lots of useless hardware in 10 years. Whereas, like, that may not be the case for CPUs. All right, let's keep going. So early computers such as the Mark One, yes, the Mark One, it's the best. It was probably the best architecture of all time, the fastest and most efficient. All right, so it's essentially like a very expensive calculator. So this essay begins by acknowledging a crucial paradox. So machine learning researchers mostly ignore hardware despite the role it plays in determining which ideas succeed. In section two, we ask what has incentivized the development of software, hardware, and machine learning research in isolation. Uh, Considers the ramifications of this styled evolution with the example of early hardware and software lotteries. So today, the hardware landscape is increasingly heterogeneous. This posits that the hardware lottery has not gone away. All right, I totally agree with this premise, but let's keep going. And so Charles Babbage's difference machine was intended solely to compute polynomial function. Mark I was a programmable calculator. Rosenblatt perceptron machine computed a stepwise single-layer neural network. Even the Jacquard loom, which is often thought as one of the first reprogramming machines in practice, was so expensive to rethread that it was typically threaded once to support a preset of fixed input fields. Oh, interesting. So this is gets back to the single input, single data. So that's sort of a model that's not very useful because like once you know the result of a computation, why would you keep running it on the same data? It's not a computer. I guess at that point it's more of a dumb automaton. But yeah, I mean like I'm not gonna shit. Like, I mean, I probably wouldn't even myself be able to build something like this even today with modern computers, from scratch. So I'm not gonna shit too much on people in 1888. All right, so the specialization of these early computers was out of necessity and not because computer architects thought of one-off customized hardware was intrinsically better. Uh, when we talk about human intelligence, the prototypical image that probably surfaces is this cartoonish blob. So in contrast, it's largely due that was made and incentivized hardware software. Okay, general purpose era. So the general purpose computer era crystallized in 1969 when an opinion piece by a young engineer called Gordon Moore appeared in Electronics magazine with the title Cramming More Components onto Circuit Boards. So Moore predicted that you could double the amount of transistors onto an integrated circuit every 2 years. Uh, so Moore thought it would sell more chips. However, the prediction held and motivated a remarkable decline in the cost of energy. Oh, interesting. Yeah, I'm gonna write this down. Like Moore was good at marketing. I lost my pen nib. Fortunate. Hmm. Oh, there. Ah, sorry about that, everyone. All right. So I'm just gonna write down here like Moore was, beast at marketing, which is sort of, by the way, a very common trend. Like whenever I sort of research like these sort of old famous geniuses, like they all tend to be good writers and compelling at communicating like why what they do is interesting. So Moore's law combined with Dennard's scaling enabled a factor of three magnitude even. So even processors demand higher performance. Uh, okay. So the emphasis shifted to universal processors, which could solve a number of myriad of problems. So why experiment on a more specialized for an uncertain reward when Moore's law allowed chip makers to lock in predictable soft margins? Oh, interesting. The few attempts to deviate and produce specialist computer for research were financially unsustainable and short-lived. So a few very narrow to tasks like mastering chess were an exception to this rule because the prestige and visibility of beating a human adversary attracted corporate sponsorship. Holy shit, I guess like this is like the so this is the Open AI and the DeepMind business model. It is old. That's kind of cool. Okay. So treating the choice of hardware and as independent has persisted until recently. Producing a next generation chip costs $30 billion and 2 to 3 years to develop. So these formidable barriers to entry have produced a hardware research culture that might feed feel odd or perhaps even slow to the average machine learning researcher. So while the number of machine learning publications has grown exponentially in the last 30 years, the number of hardware publications have maintained a fairly even cadence. For a software company, leakage of intellectual property can make or break the survival of the firm. This has led to much more closely guarded research culture. Oh, interesting. Uh, Interesting. Yeah, I mean, this is sort of so hardware is slow and closed, software is fast and open. So, in the absence of any lever, machine learning researchers rationally began to treat hardware as a sunk cost to work around, uh, as opposed to something fluid that could be shaped. However, just because we have abstracted away hardware does not mean it has ceased to exist. Uh, okay, great. So the hardware lottery. So I suppose it is tempting if the only tool you have is a hammer to treat everything as if it were a nail. I mean, this is sort of like an important thing because like your tools so your tools shape how you think in general. The example I like to give here is like when you look at stuff like, I don't know, let me show you I guess it's pretty good in DaVinci Resolve, for example. So like in video editing, for example, they'll have like, okay, import your media, cut cut your video, edit it, correct the color, fix the audio, publish it. So DaVinci Resolve explicitly has these each as tabs. And so this is sort of the model they want you to work with, like do these things in this order. Whereas like in Photoshop's case, like there isn't sort of this natural step-by-step thing you do. It's like, okay, here's a bunch of tools, do what you like. So it feels a lot less structured. Uh, but I guess like the tools are very different. It's just like sort of a beginner's impression of both. However, it only takes one of these aspects to be present. Okay, so despite our preference to believe an algorithm succeed or fail in isolation, history tells us that most science breakthroughs follow the Anna Karenina principle. So successful breakthroughs are often distinguished from failures by benefiting from multiple criteria aligning surreptitiously. For AI, research this often depends upon winning what this essay terms the hardware lottery, avoiding possible points of failure in downstream hardware and software choices. So an early example of the hardware lottery is the analytical machine. So Charles Babbage, so it was never built in part because he had difficulty fabricating parts with the correct precision. So, but this electromagnetic technology to build the theoretical foundation laid down by Babbage only surfaced during World War II. Okay, so as often noted in TV show Silicon Valley, often being too early is the same as being wrong. Ouch. Yeah, from personal experience, I will agree this is a painful, it's a painful reality. Uh, but when Baggage passed away in 1871, there was no continuous path between his ideas and modern day computing. So the concept of a stored program, modifiable code, memory, and conditional branching were rediscovered a century later because the right tools existed to empirically show that the idea worked. I mean, yeah, this is sort of maddening when you think of it, right? Like, let's say you're someone as brilliant as Babbage and you're doing all this cool shit, but then you think some of your ideas failed, but they only end up being relevant 100 years later. Uh, I mean, it sucks. Like, let's be real. Like, yeah. So perhaps the most salient example of the damage caused by not willing the hardware lottery is the delayed recognition of deep neural networks as a promising research direction. So backpropagation, invented in 1963, reinvented in 1976, and again in 19. How many inventors are there? So, however, it was only 3 decades later that deep neural networks were widely accepted uh, as a promising research direction. So, this gap between algorithmic during the general purpose era, hardware like CPU were heavily favored and widely available. So, this is known as the von Neumann bottleneck. The available compute is restricted by the lone channel between the CPU and memory along which data has to travel sequentially. Oh, interesting. So, the von Neumann bottleneck was terribly ill suited for matrix multiplies, a core component of deep neural network architectures. Thus, training on CPUs quickly exhausted memory bandwidth, and it simply wasn't possible to train deep neural networks with multiple layers. The need for hardware that supported tasks with a lot of parallelism was pointed out as far as back as the early 1980s in a series of essays titled Parallel Models of Associative Memory by Hinton and Anderson. Holy shit. Whoa. Okay, so I'm just gonna write this quick note. So the limitations of CPU and the Neumann bottleneck or DNN uh, was obvious in 1989. I mean, it's a long time spending to be wrong. Like, I wonder why didn't any of these guys win Turing Awards? What do they do? K and Piske. What do they do? K and Piske. What? Learning matrices and their applications. Oh, that's an interesting title. What? They're barely cited? This really blows, actually. Come on, you just like invent this shit and then you get 100 citations. Like I've seen way more mediocre papers get way more citations. Fuck man, the world isn't fair. It sucks. The very first neural networks paper has 140 citations. Some that came 10 years later have 1,000. World's not fair. All right. Just gonna write down a note here. So Piske MVP. Later. Bye. So the idea of specialized hardware. So most of the attempts were actually operationalized, like the connection machine, 1985. A ring array processor, the Japanese fifth generation, were designed to favor logic programming such as Prolog and Lisp that were poorly suited for connection deep neural network. Oh, interesting. They're also like Lisp machines. So it took a full hardware fluke in the early 2000s, a full 4 decades after the first paper about backprop, for the insight about massive parallelism to be operationalized in a useful way for connectionist deep neural networks. So many inventions are repurposed for means unintended by their designers. So Edison's phonograph was never intended to play music. He envisioned it as preserving the last words of dying people or teaching spelling. In fact, he was disappointed by its use playing popular music as he thought it was too base an application for his invention. That's interesting. Diamond a similar vein only began to work with when a repurposed technology was unexpectedly repurposed. I mean, yeah, like the graphic, like Nvidia sort of hit a gold mine, or maybe that's not true. Like, I mean, what's interesting about what Nvidia did was they just figured out, like, I guess, like a good sales strategy. They had good libraries and got good like sort of dev buy-in for people to wanna experiment with it. I think it would be BS to call it a fluke, because if it was a fluke, why did another hardware architecture not succeed more? They're far better at paralleling sets of single decomposable instructions such as matrix multiplication. Okay, so then Persefci, oh wow, it's a comparison of now famous 2012, which used 16,000 cores to class pay sure to a myriad to solve the same task with only 2 CPU cores and 4 GPUs. Lol. Well, I mean, sort of the difference in scale is just remarkable, right? Like we're talking like 16K to, you know, two CPU cores to six. So Lisp was the dominant language for AI intelligence. It's particularly suited to handling complex logic expressions, which are a core component of reasoning in expert systems. So software also plays a role in deciding which research ideas win and lose. So Prolog and Lisp were two languages heavily favored until the mid 90s in the AI community. So for most of the peer students of AI, we expected to actively master one or both of these languages. Oh, interesting. Colobert. Oh, interesting. Like, it took a long time to get basically the DNN library. So basically, it was MATLAB, then Torch. I'm sort of curious here with the original Torch paper it's saying it's Colobert. That sounds French to me. Colobert, Torch. Roman Colobert. Looks like he's an early NLP guy. Okay. I mean, sort of like I'm sort of nerding out at this point. Let's like finish. We can finish the paper and then just like sort of end off on a discussion and on high level thoughts. So when there's a loser, there's also a winner. Uh, that the statements that were well suited to Prolog. Oh, I see. Basically, uh, they had like complex logic systems. Lisp and Prolog. All right. So today there is a renewed interest in joint collaboration between hardware and machine learning communities, include changing hardware economics prompted by the end of Moore law and the breakdown of Dennar's scaling. So bigger is better raised the number of model parameters that has gripped the field of machine learning. The end of Moore's law means that we are not guaranteed more compute hardware will have to earn it. To improve efficiency, there is a shift from task agnostic hardware like CPUs to domain specialized hardware that tailor the design to make more tasks more efficient. So the first examples of domain specialized hardware were released over the last few years. So we have the TPUs, edge TPUs, ARM Cortex, Facebook's Big Sur, optimized explicitly for costly operations to deep neural networks like matrix multiplies. All right, fair enough. So it like to me at least, it always seemed like TPUs was sort of and basically remove all the graphics stuff, keep the matrix multiply, add some extra stuff for deep learning like a hardware kernel for sigmoids and all that stuff, and make it faster. I'm sure there's more. Like someone's gonna come yell at me and say you don't know what you're talking about. But it does fit this trend where it's specialized, but it's incremental. However, even though it's specialized and incremental, given that Google at least is running these workloads at just these insane scales. Probably it pays off for them actually in the very short term. I don't think they're waiting years to make back their return on investment in this case. So unstructured pruning and weight-specific quantization are very successful compression techniques, but are incompatible with current hardware and compilation kernels. Oh, so this is, for example, stuff like when we get to like B point or or a floating point. Uh, but in both of these cases, like we don't know what level of precision works best. Like in the case of machine learning, you don't need uh, like a super high range. You just need like good precision. And so in that case, like you may not want something that's sort of like, but the opposite could also be true. Like either or would be something fairly reasonable. Can I zoom in on the paper? Yes. And let me make my head smaller. All right, excellent. So yeah, let's see. Some of these designs that facilitate sparsity have already hit the market. So the point about sparsity is interesting because when you think of like, let's say you have like in any like I've sort of made this point already in that like I like to think of a network as the combination of as a composition of several layers where each layer is a continuous function and each function is basically a matrix. So like we can just say something like this. And if you actually look at each of these matrices, they're actually fairly sparse. Like it'll look something like this, like by dot, I essentially mean something that looks like a zero, and then it'll look something like this, and then, three like this. I mean, typically these are values between 0 and 1, then, something like this. So most of it is zero. And again, like GPUs in particular weren't designed with this sort of sparsity in mind. And so you end up with a conflict where it's like, well, yes, it does run fast on a GPU right now, at least faster than a CPU. But if you were to design it from the ground up for sparsity, which is more common in machine learning than dense data, you would you know you would just not design a GPU the way you did today. Um, yeah. So hardware is catching up to the present state of machine learning. If the lifetime of a use case lasts more than 3 years. So betting on ideas that have longevity is a key consideration for hardware developers. So this is a great point. Like overall, like they mentioned this like way up in the paper, but like the cost of designing a new chip is on the order of like 80 to $100 million, and it takes about 3 to 5 years to see it to market. And so if that's your constraint, like you better be really sure that what you're building is going to last in 3 to 5 years. However, in software, you take the complete opposite approach where it's like, well, you don't really know what's going to be big in 3 to 5 years. Therefore, you make many small bets. And the first one that picks off in a big way, you fully invest in. So it's a total change in attitude. Like there's no move fast and break things. There's no let's be open each other and share work because if someone is richer than you and copies your hardware ideas because they're better there, like they are going to beat you. Whereas with software, it's like there's so much going on that the cost of you getting an idea poached isn't that big a deal because there's loads of ideas that exist. So matrix multiplies are a safe target to focus, anchored by the widespread. Okay, yeah. So they talk about this quite a bit. Like basically, GPUs are really good at this fast matrix multiplication. Maybe I should just make a quick note as to why I think that would be interesting because I've just been saying this as an assumption. So let's say you have two matrices that look like this, right? And then it looks like this. And then you can think of so like you're gonna have a bunch of rows. I'm just gonna make the rows look different, just so that let's say this is the first row, and then this is the first column, right? And then this is the second row, and then this is the second column, for example, right? And so the idea now is that what you can do to actually compute the values in these matrices is that this operation you can do like basically this times this, you can do without caring what the other values are. And so if you allocate each of these row by column operations on a different GPU core, you're going to see the performance become drastically better. And GPUs have on the orders of thousands of cores. So now if you have a matrix that's like with thousands of rows and thousands of columns, it's going to run blazingly fast just because of this inherent parallelism. Um, and so this is sort of like the main idea behind like parallelized matrix multiply. And so when you hear people say like stuff like, well, GPUs are really good at matrix at deep learning, what they're really saying is GPUs are really good at matrix multiplication. And because most modern deep learning is focused on the composition of multiple matrices, like each layer is a matrix, GPUs are really fast at deep learning. But again, we get back to this point of, well, if this wasn't the best way to learn stuff in general, if this wasn't the best way to do uh, object detection or language models or what have you, how would you know if you don't have hardware that can run this new algorithm really fast? And the short answer is you don't over at least short periods of time. You can only know that over longer periods of time. So time tells you which ideas are good and which ideas are bad. So that's sort of a very humbling thing. But in general, like I mean, even though we're in a very fast moving field, like ultimately I would expect like most of my opinions are going to be wrong in like 5 years in software. And that's just sort of like one thing you need to keep in mind. And it also sort of encourages this trying out a bunch of stuff approach and investing in multiple smaller projects, which you can't do in hardware. Actually, in hardware, if you're wrong, it's very costly. Like you lose your business. In software, if you're wrong, it's fine. You can just pivot to something else. So there are still separate questions for whether hardware innovation is versatile enough to unlock or keep pace with entirely new machine learning research directions. All right, fair enough. So the inherent challenge of this task, so in a paper published called Machine Learning is Stuck in a Rut, the authors considered the difficulty of training a new type of computer vision architecture called capsule networks on domain specialized hardware. So they include novel components like squashing operations and routing by agreement. So these architecture choices aim to solve for key deficiencies in convolutional networks like lack of rotational invariance and spatial hierarchy understanding. Okay, let's talk about this a bit. So typically, like when we work with images, okay, you can think of an image at least like let's say a black and white image that makes it simpler. Like it's a sort of a 2D matrix with some pixel values. Like let's say 1, 0.2, 0.5. So the higher the value, the more likely this is to be like white or black. And then, sorry, like 0.5 would be somewhere in the middle. And so, given that you're going to have shades of gray and shades of white, you're going to end up with like some sort of image. Like, let's say you end up with something like this, right? Uh, so the idea with convolutional neural networks is that let's say you work over this image in patches, and for each patch, like let's say you're going to look here, instead of having like a bunch of pixel values, like let's say 1 and 0.2, you're going to either take like the max or the average of them. And so you end up with a new smaller compressed image that may just have like the bigger values, like let's say 0.2 and 0.5 in this case. What's sort of interesting about this sort of architecture is that it is uh, rotation invariant, as in if you flip the image, uh, then the matrix that you get after convolving will be the same as if you had, let's say, done the convolution then flipped, or flipped the image and then did the convolution. So it ends up working out the same. That's called, translational invariance. Rotational invariance would be you shift it 45 degrees, and then in that case, it's no longer true. I mean, this is sort of a longer talk, but I can talk about CNN some other time if you're interested. But it's just to give you an idea. Like, I mean, there are some desirable properties, like like rotational invariance that we would like in machine learning models, but we cannot implement them efficiently because it's not obvious how to scale that to a GPU. So the research just stops. Like we go like, well, this is a bad idea. Well, no, it's actually a great idea. You do want translation like rotational invariance in your models. So whether or not you agree that capsule networks are the future of computer vision, the author says something interesting about difficulty of trying to train a new type of image classification architecture on domain specialized hardware. So they've prioritized delivering on commercial use cases while built-in flexibility to accommodate the next generation of research ideas remains a distant secondary consideration. Yeah, so to me, this is just a symptom of like zero risk. Like, if you're Nvidia, at this point, you don't want to take risk. You just want it to be, you want the same thing to be faster. So it prompts the question of how much researchers will implicitly overfit the ideas that operationalize well and available hardware rather than take a risk on new ideas. Okay, I actually think this is not an open question as far as I'm concerned. I think people will take less risks because their careers depend on it. Like ultimately, like you have to look at what like how is a scientist or a machine learning practitioner rewarded in practice. If you're a researcher, like what you really want, like sort of the holy grail for you is I got state of the art on some really well known data sets. Like my algorithm is the fastest or it's the highest accuracy one. Uh, and so even if you try out like some wacky idea that doesn't work as well, like why would you do it? Like you can do it if you already have tenure or if you don't care about prestige or getting a nice research job at Google Research. But for the most part, you do. Like I mean, I think sort of telling people that hey, you should pursue something that's against your best career interests. I think this is a losing value proposition, except for a few unique individuals, or for people willing to do what I talked about earlier, which was sort of this barbell strategy where you invest some time in incremental ideas and another chunk of your time in risky ideas. But hardware manufacturers are certainly not doing this, just to be clear. Where were we? All right. So, oh yeah, and by the way, this is true for industry as well. Like in industry, like you want to be the guy as a scientist to come into your boss and be like, well, like that this algorithm that we were running in production had an accuracy of 80%. You know, now it has an accuracy of 85%. Like the added complexity or the training time or the cost that you added. These are all important considerations, but ultimately, that one metric will sort of determine your value as a scientist more so than others. And so it's again like another very direct signal or feedback loop to you that's saying you should take less risks, you should take results, or else like your boss and peers won't be happy. So it is an ongoing open debate within the machine learning community about how much future algorithms will differ from models like deep neural networks. So the risk you attach, depending on domain specialized hardware, is tied to your position on the debate. Yeah, this is a good point actually. Basically, I mean, if you're in the business of selling GPUs, you're gonna say dense deep neural networks are the future. And so it's sort of really hard. Like you get back to this point where, like, before you trust anyone, like you have to look at what are they trying to sell you. And I think this is true for any hardware manufacturer. Like they're just going to tell you the best algorithms are the ones that our architecture supports best. So several major research labs are making this bet, engaging in a bigger is better race in number of model parameters and collecting even more expensive data sets. So for many subfields, we are now in a regime where the rate of return for additional parameters is decreasing. So the training of GPT-3 alone is estimated to exceed $12 million. Damn, son. I mean, here's the thing. Like, I think another people think don't consider is they go like, oh my God, like, OpenAI spent $12 million on running this model. Well, it sort of makes more sense if you view the business as well. OpenAI is not paying a premium for these, right? Like OpenAI is either getting a good deal from NVIDIA directly or a deal from Microsoft directly to say we're training on the intelligent cloud or what have you. And so the main business model of OpenAI is a media company. And so if the PR of $12 million generates enough hype for OpenAI, which it has because every single machine learning researcher has been talking about OpenAI for the past couple of months, then it was worth it. I mean, but if you think of it as, hey, I want to train a language model to, for example, better tag these contracts that I have and with the customer I'm working with, then it's not worth it because you're going to spend all that money. You're not going to get the cool marketing hype, and maybe the results will be incremental. But if you're Microsoft, if you're Google, if you're Nvidia, you're in a different business. And so this gets back to a sort of perverse incentive. But if you're in the business of selling cloud services, or if you're in the business of selling GPUs, you have an incentive to say bigger is better. So human brains, despite their complexity, remain extremely energy efficient. Yeah, so this is something people talk a lot about, and that like, oh, like neural networks are like the brain. Like, no, they're not, because like neural networks consume way more power than brains. They use something else. It maybe looks like a neural network because it has the name neuron in it, but that's sort of where the analogy drops. I think neuroscience research is going to take a while. I don't know what's going to happen in the space. I researched biotech quite extensively when I was in grad school, but I don't want to comment about this since it just gets very extremely hand wavy. So biological examples of intelligence differ. Okay, our brains are able to learn efficient representations with fewer labels. Yeah, I mean, debates like debatable here. Like I would say on one hand, for example, like when I think of some animals, like a cat, for example, you're a kitten, you're just born, and you already know, like this is you can walk around, it's dangerous. Yeah, you need your mom for milk, but for the most part, you're fairly independent. Whereas like a human child seems to require like about 18 years worth of training data before they're allowed to even make independent decisions. Uh, and so it depends. I mean, and so like now we're talking data volume, right? So let's say if I were to compress everything I read from when I was year zero till year 18, along with highly streamed, like 8K resolution video footage of my environment, like if I were to take, that aggregate, all of that data and the aggregate of all the data that people have fed to me and the work they did, I doubt it would be that memory efficient or compute efficient. I would say it's probably equally costly, but to be fair, one interesting compressing technique that humans have is like heredity. Like you can teach other people stuff in a simpler way, and as far as I know, there's no simple way to do that in neural networks. So the way we compress information is via multiple generations. This got very deep, yo, philosophical and shit. Um, anyway, humans have highly optimized. Our brains are able to fine tune. That's all fine and good. That we are clearly out of the model of intelligence and success. It may not be the only way. All right. So scientific progress occurs when there are influence factors which allows the scientists to overcome the stickiness of the existing paradigm. So the speed at which much better California. What's the CA? So the speed at which paradigm shifts have happened in AI research have been disproportionately determined by the degree of alignment between hardware, software, and algorithm. Thus, any attempt to avoid hardware lotteries must be concerned with making it cheaper and less time consuming to explore different hardware software algorithm combination. All right. So this is interesting. So this leads back to this so this leads back to an interesting discussion around, well, how can hardware be cheaper to experiment with? So there's a few things I'm optimistic about here. So some is like, let's say Arduino, which is maybe not all that useful for machine learning, but at least in the case of robotics is. And the other is FPGAs, which you can think of as like hardware that you can program. But while FPGAs work great for prototypes, they still are really expensive to use at scale. Like you're not going to train GPT-3 on FPGAs. Like people talk about this shit a lot. I don't know anyone who actually does it or is willing to spend the money for it. And I'm guessing there's probably good reasons for that. But still, I like that about FPGAs. I like the fact that, this overall trend that I like to call turn, you know, hardware problems into software problems. This overall, I think this idea is very powerful. And you can sort of see it in robotics, for example, where, like, let's say making a robot simulation in the real world is expensive, it's dangerous, the parts cost hundreds of thousands of dollars. The incremental cost of training a new robot in software is pretty much zero. It's just like, and so this is sort of something you can do. And I would expect, like, hardware design to sort of, or at least maybe I don't expect it, but I want it at least. So yeah, so now talk about this again. So producing a new chip costs 30 to 80 million dollars and takes 2 to 3 years to develop, and the fixed energy costs of building a manufacturing plant are enormous, estimated at $7 billion. Holy shit, man! So really, like who has $7 billion to just drop on a factory? Like to me, that seems like either you're a government or you're just like this massive conglomerate. But I don't see any, I don't know, talented hardware guy going into something like YC and being like, hey, Paul Graham, can I grab $7 billion? Wow. Okay, that's a lot bigger than I expected. If I'm being honest, like it just makes me think, like I don't know, like where I'm like, do you know, like let's say the incremental cost of starting like a business, like an insurance company or a bank, is it similar? Like, is it really just software that's cheap, or is it that all businesses except software are cheap. So experiments using reinforcement learning may help decrease the cost. Yeah, so I've seen a bunch of stuff like this, a new MSR paper that talks about how to efficiently allocate different parts of a chip. Yeah, and then they talk about FPGAs, like I was saying, coarse grain, and so this is all used in crypto as well. It's billions for most industries. It really sucks, man. I wish I was just rich and could just like do this stuff for free. So these devices allow the chip logic to be reconfigured to avoid being locked into a single use case, and the trade-off for flexibility is far higher, and the need for tailored software development and coding even simple algorithms on FPGAs remains very painful and time-consuming. So true. Specialized hardware is almost directly leads to harder to program. Like this is sort of like almost axiomatic. Like so, in the short to medium term, hardware development is likely to remain inexpensive and prolonged, and the cost of producing hardware is important because it determines the amount of risk and experimentation. So, investments in hardware to deep neural networks is assured because our concurrence to have enough commercial use cases. Okay, the bottleneck will continue to be funding hardware for use cases that are not immediately commercially viable. These more risky directions include, I like this, yeah, neuromorphic, optical, and quantum computing. So basically, these are like I would call them like the non-sexy compute models. That would be huge. I mean, like, so let's just sort of talk about these very briefly. Um, so biological hardware, I think, is sort of interesting. It's almost sci-fi, but like cells have logic. Like you can, for example, take various cells and proteins and then like program them to add numbers. It's extremely convoluted. I don't know how the fuck you'd actually build a computer with stuff like this. But to me, it's very cool. Like I actually have a book called like Programming Synthetic Biology. And there's people that do this. I think it's incredible. But as far as I know, they're still building simple stuff. Another thing we can talk about is like analog computing. So analog computing is interesting because most computing you do is digital. So you mean like what the fuck analog? Is that vacuum tubes and is it slow? Actually, it is not. Analog computing is actually the domain standard when it comes to like let's say hardware and signal processing, because as opposed to working with bits and then converting them to real signals, your computer just works with signals and does signal processing really fast. There's people that also believe that you can work with these signals really fast and also do digital computation faster with it. And so your computer is basically just like the series of lasers and mirrors communicating with each other. And I think that's a very interesting research direction that I would like to pursue more in my spare time, but I will say the math there is very dense. Uh, Quantum computing is basically, programming with quantum bits. As far as I know, the main application there is pretty much just breaking cryptography. So, like, so I don't know if any positive use case for it besides modeling quantum systems. I say there's one very negative use case for it, which is like all of your passwords become useless. So I don't know like how that's gonna play out. Like I keep seeing that it's coming soon. It's not coming soon. Neuromorphic computing is basically uh, hardware that's inspired by the brain. So, for example, as opposed to having libraries that can do neural networks really fast, maybe you want to do spiking neural networks really fast. And basically, the difference is like with a neural network, sorry, with a spiking neural network, like this is sort of what the response looks like. So, let's say this is time and this is voltage. If you give a spike to a neuron, what it does is it spikes up, then it goes down, and then it goes like this. And so by that I mean it doesn't just go like this, like in a straight line. So some people believe that just by virtue of this, that it'll be more memory efficient to train. Hey Sudamace, nice to see you on stream. So some people believe that just by virtue of having this sort of spiking neuron, that your models will be faster or trained with less memory. I personally find this claim extremely questionable. It's sort of like I don't know. I feel like there's just absolutely no basis to even make that claim. It's just I don't know. It's just it's like the brain. It must be good. Well, I don't know. Like you could also make Jello, but it doesn't mean it's gonna compute stuff like the brain. Um, so there's a slow interest in which was $1.5 billion in funding for micro electronic technology research. Actually, this is a good question for Stefan. Like, do you know if like historically, did all hardware startups start with massive government subsidies? Uh, like that's like I think another thing I'm curious about because it definitely seems now they're saying like, oh, $47 billion. What? I like what the fuck are these numbers like? All right. Oh, nice. We're almost done. So design remains risk averse due to the large amount of capital and time required to fabricate each new generation of hardware. So, an interim goal is to provide better feedback loops to researchers about how algorithms interact. There's no easy and cheap to use interface for benchmark algorithms against multiple types of hardware at once. There are frustrating differences. Software kernels are optimized with different hardware. Yeah. This gets back to the point. Like, uh, hardware should be uh, as easy as software. Like that's the only way you get to solve this problem. I mean, so yeah, like funding overnight. Yeah, so I guess the ones I'm thinking about are Nvidia, ARM, Intel, HP. All these hardware manufacturers. Like, I'm just curious if they also sort of started in garages or whether they just had like big funding from the get go. I think HP was original garage startup, if I'm not mistaken. It sort of I think started the Silicon Valley ethos. So these challenges are compounded by an ever more formidable and heterogeneous landscape of hardware. So as the hardware landscape becomes increasingly fragmented and specialized, fast and efficient code will be required, ever more niche and specialized skill. Uh, yeah, this is sort of one of the things that blows about this. Like, let's say a new hardware architecture comes out and you want to build algorithms for it really fast. Like, odds are you need to spend years of your life doing it. Because if it's not like the CPU, if it's not exactly like the GPU, the learning curve is usually like pretty intense initially. So one way to mitigate this need for specialized software expertise is focusing on development of domain-specific languages, which are designed to focus on a narrow domain. A promising direction is automatically auto-tuning the algorithmic parameters of a program based upon downstream choice of hardware. Okay, so this is sort of what I'm going to summarize these. So this is saying make compilers better. My handwriting is garbage. Uh, and then make the languages better. None of these solve this problem. Like these all make it better to deal with, but there's still someone that needs to deal with this abstraction. Like even though you, as if you're not working with compilers directly, you're working with some compiler that deploys your code to multiple hardware. Sure, you're gonna get results really quickly, but then if you actually want this thing to run really fast, you generally need to go down very quickly. Unless you're just like, running a code and okay. So Pseudomaze is saying so okay, so Veram is saying that they typically raise billions in private funding overnight. So this is to the point as to how do hardware startups get started. And so Nvidia started than any other SV startup. They were lacking in funding in the beginning, first 5 years, and they have an interesting story, and the industry was against their model of building hardware. So what I know about Nvidia is that they took a sort of academia first approach, as in they were going to academics and then helping them figure out like what kinds of use cases can you unlock with GPUs. I think that's a great strategy because I think if you go to industry directly, they're going to say, well, the incremental cost of training my workforce to rewrite your algorithms is one, uncertain, two, more complex. I need to work with you on your libraries. Why would I do that? I already have a partnership with Intel. Like, I think the discussion probably goes something like this. But, to be fair, like, it's kind of crazy, like, seeing NVIDIA, the origin versus now. Like, I would say, like I know like Jensen's like kind of insane, right? Like it's like one his company builds cool stuff. He's sort of an interesting showman and presenter himself. He's a good memer. Actually, like by the way, I'm even using NVIDIA Broadcast right now. That's how I'm getting the blur in the background. I also have an air conditioner blasting right next to me, which I suspect you're not actually hearing. So it's just insane to me that these are just things you can do with GPUs nowadays. Like it's just like, oh, it's just matrix multiplies. Sure, but you can do a lot of shit with matrix multiplies. So I think that's the story there. Like I mean, obviously we're in a local, uh, you know, maybe I'll just do this for now. So let's see here. Yeah, I mean, so obviously we're in a sort of local. You see like the quality of the camera, you see the blur. It's like it's gonna make you think like I have some sort of crazy DSLR. I don't. I just have a webcam. It's a Logitech webcam with machine learning making the nice blur. Um, so overall, like I would say for me, the general story with this whole paper is something I've been thinking a lot about. Is that yes, you get diminishing returns from investing in the same hardware and architectures that may not be the best ones. However, it's sort of like you have to have enough money and enough time to sort of out survive the market. As in, well, like if for the next 10 years, optimizing GPUs is going to continue letting people get promoted, get better careers, get best paper awards, it's going to take a long time before you can sort of do these very different and like unique architectures that may work better for some machine learning use cases. Uh, but yeah, I mean, like I think it's all about like, that's why like risk taking is called risk taking, right? Like you take a risk, it is probably not going to pay off in this case. There's sort of a like a bitter truth. Big production, yeah, you see this? Like it's just like with one button click on Streamlabs, and I can adjust back and forth and stuff. So I have a professional studio here. I bought a green screen by the way, but Jensen also made that obsolete. Uh, but yeah, guys, I think like for me, let's sort of like the story here is you want to take risks, but it's not obvious like on which time frame they'll pay off. So you want a barbell strategy. Like you want to know just enough about the existing techniques to be dangerous, to do useful stuff, to make money, to make your customers happy, to make your boss happy, to make your advisor happy. But in the meantime, try to invest a small fraction of your time, let's say Fridays, maybe Thursdays as well, and weekends, to invest in new stuff. Because if it does pay off, it pays off big. And worst case, you just have an interesting story. So thank you so much, guys. Like I had a lot of fun. Like special shout out to Varam and Pseudomaze for checking in. Thank you so much, everyone. I think I'll probably do another stream this weekend about other related topics related to unique architectures. So I'll just keep you posted and stay tuned on my Twitter account where I'll be announcing the kinds of streams I'm thinking about. Thank you so much, everyone.